Right, so in this video I'm going to look at proof by induction for inequalities, and I'm going to look at proving by induction that 2 to the power of n is greater than or equal to n squared, where n is greater than or equal to 4 and n is a natural number. So again, we have 4 steps. I'm going to do step 1 first, and that is to show that the proposition is true for the lowest value of n that we're dealing with, and that's 4. So stick 4 into both sides of your inequality, so you get 2 to the power of 4, which is 16, and on the right hand side you'll get n, which is 4 to the power of 2, and that's also equal to 16. So 16 is greater than or equal to 16. So hence the proposition is true for n is equal to 4. Now, step 2 then is to assume the proposition is true for n is equal to k. So 2 to the power of k is greater than or equal to k squared. So we're assuming that this is true, and again step 3 here is to prove that the proposition is true for n is equal to k plus 1, given that we're assuming that it's true for n is equal to k. So in other words, 2 to the power of k plus 1 greater than or equal to k plus 1 squared. Just put in a k plus 1 here and here. This is what we want to prove. Now, let's start the proof then. Okay, so if we take the left-hand side, so we're taking the left-hand side of this here, we've got 2 to the power of k plus 1. We can break that up into 2 times 2 to the power of k. In other words, this is 2 to the power of 1, this is 2 to the power of k. Multiply these two together and you'll get 2 to the power of k plus 1. That's one of your rules of indices. Add the powers when you've got the same base here of 2. Now, 2 times 2 to the power of k should be greater than or equal to 2 times k squared. Why is that? Because our assumption here, if you look at our assumption here, 2 to the power of k is greater than or equal to k squared. So twice 2 to the power of k should still be greater than or equal to twice k squared. So we just multiply both sides by 2 if you like. But this is what we want to prove here, and all I've done here is just simply split this up into 2 times 2 to the power of k. And that should be greater than or equal to 2 times k squared. So that's our left-hand side there. If I take the right-hand side of our inequality that we want to prove here, so the right-hand side of our inequality is k plus 1 squared. That's just k squared plus 2k plus 1. When you square k plus 1, you get k squared plus 2k plus 1. Now, on our left-hand side, we've got 2 times 2 to the power of k. We know that that's greater than or equal to 2k squared. So if we can show that this here is in fact greater than this here, then 2 to the power of k plus 1, or 2 times 2 to the power of k, will be bigger than this. In other words, it's like saying, for example, if a is greater than b, and we know that b is greater than c, then a must be greater than c. If that number is bigger than that number, and then that b there is bigger than another number c, then the first number must be bigger than the last number. So that's all we're doing here. We've got this bigger than this number here, or equal to it, and I'm going to start proving here now is that this is in fact greater than this here. So let's start doing that then. So what I want to try and prove here, what I want to try and show here is that 2k squared is greater than or equal to k squared plus 2k plus 1. If I can show that, then this here will be true. So let's just bring these over here. Let me see, subtract these from the right hand side. 2k squared minus k squared will give me just simply k squared minus 2k and minus 1 greater than or equal to 0. So all I've done is subtracted this from the right hand side. Now, if I can show that this is true for k, then I'll have proven my k plus 1 proposition here. So let's have a look and see if we can prove this. Well, this is a quadratic, so what I'm going to do first of all is just see where this cuts the x-axis, if you like. So I'm going to assume that it's equal to 0 first. So what I'm going to do is, let's do k squared minus 2k minus 1 equal to 0. I just want to see where this cuts the x-axis. So if I try to do this using brackets, it's not really going to work. So what I end up doing here to solve this for k is to use the minus b formula. So here we've got a is equal to 1, b is equal to minus b is equal to minus 2, and we have c is equal to minus 1. So we know here in this case that k will be equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So when we put our values into this formula here, we'll get, let's see, minus b, so minus minus 2 is just 2, plus or minus the square root of b squared, so that's minus 2 squared, minus 4 times a, which is 1, and c, which is minus 1. And all of that is over twice 1. So if I do that, I get 2 plus or minus the square root of 2 2s are 4. Minus minus is plus. So I'll get this square root of 8 here if I do that. 2 2s are 4. 4 times 1 is 4, and that's a plus. So yeah, 8. So here I'll end up with 2 on the bottom. Now if I do that, I get 2 plus or minus root 8 is just 2 root 2 over 2. Divide that into both sides here, and I just get 1 plus or minus the square root of 2. So in other words, my quadratic will look something like this, where this is 1 minus root 2, and this here will be 1 plus root 2. Now if I go back to my original inequality, all I've done in this part here downwards is to find where this particular quadratic cuts the x-axis, and I've done that. So I go back to my inequality, this part here. This is what I want. This is what I want to prove. Now, if I look at this here, I want this here to be greater than or equal to 0. I want y to be greater than or equal to 0. So I'm looking at these values up here and these values up here. All the y values here will be greater than or equal to 0. The x values associated with that will be all of these x values down here and these x values up along here. If I'm talking about any of these x values or these x values here, I'm going to end up with this being true. Now we have to remember that our k, our original k, has to be greater than or equal to 4. Now 1 plus root 2 is, let me see, 1 plus root 2 is about 2.4. So this is roughly equal to 2.4. Now, if my k is always greater than or equal to 4, I will always end up somewhere up along here on the graph. So in other words, wherever k is greater than or equal to 4, which is the case in this entire question, this is true. K squared minus 2k minus 1 will be positive. Y will be positive. I will be dealing with values up here somewhere. So we've proven then that this is true. So in other words, our k plus 1 is true. Our k plus 1, we assumed that the proposition was true for n is equal to k, and we've just proven that it's true for k plus 1 as well. So what I'm going to do now is just have a look at step 4. I'm just going to write out step 4 here. So that's step 4, which is just the final step. So it's just really making the statements here. So what we're going to do here is just say that the proposition is true for n is equal to 1. The proposition is true for n is equal to 1. We did that, sorry, not n is equal to 1. We actually did n is equal to 4 in this particular case, not n is equal to 1. We started with n is equal to 4. We've shown that, or we assume that the if the proposition is true for n is equal to k, then it is true for n is equal to k plus 1. So this is what we've proven in step 3. So therefore, the proposition is true for all n is an element of n, all natural numbers where n is greater than or equal to 4 in this particular case. Okay, so the proposition, we showed that the proposition was true for n is equal to 4. We then assumed it was, if it's true for n is equal to k, then it's true for k plus 1. This is what we proved in step 3. The proposition is true then for all values of n where n is greater than or equal to 4. So in other words, if k was 4, then it will be true for 5. If it's true for 5, it's true for 6, and so on. So that's our proof completed.